Hi, I'm Sam Roberts from Roberts Geospatial Engineering. Today I am going to show you how to do virtual gridding of LiDAR data using ProRaster Scientific. So you must start with an MRP file. Your MRP file is created using the import LiDAR operation. You'll import your LAS files and LAS files into an MRP file, and once you have that MRP file, you can then do some gridding. So the example I'm going to use today is the New South Wales Marine LiDAR from 2018. Let me just drag that into ProRaster Scientific. So this is a 73.6 gigabyte file. Let's just display it by classification index. I'm going to choose a color table that I've created for this particular file because it has extended classifications for the bathymetry returns. So there's our file, and as we zoom in, you can see that we don't just have a few points, we have billions and billions of points. And you may have noticed that there was a transition between there, where everything looks yellow, to here, where we get a whole lot of these lighter points. That's because when I've constructed the MRP file, I've directed the import to drop out some returns before it drops out other returns. So the returns that are of no value to me, unclassified returns, bathymetry returns that don't represent seafloor bed, they might be, a reflection off the surface. Those returns get dropped out first. That means by the time I go up the pyramid, I'm keeping returns that are valuable, and I don't have any returns that aren't valuable left behind. So that's going to help us when we're gridding the data at multiple different scales. Just a quick word on the MRP file. I'll go into the raster source editor here, and we'll just look at a little report on this file. So if I look at, say, the X channel, so it gives me a point count, which is 7.72 billion. This is the number of returns in this pulse return LiDAR data. It also gives me a pulse count, and there's 4.8 billion pulses, so about roughly half the number of returns. So that's what we're dealing with, 7.7 billion returns in a 73 gigabyte file. Do the maths, you get about 10 bytes per return. So if you have a standard consumer grade SSD of maximum size, which at the moment would be like 8 terabytes, then you could expect to fit onto that SSD an MRP file which might contain about 800 billion LiDAR returns, and that's about the largest that you can deal with in a consumer grade system at the present time. If you want to go to something larger than that, the system can certainly handle it, but you're going to require some more sophisticated SSD storage. So that's our MRP file. Let's now grid it. So I go to the point processing menu, virtual gridding, and slide across and select virtual grid. So here's the virtual gridding dialog. I need to select an MRP file, or I can select a raster source in which I've added multiple MRP files. So you can grid multiple MRP files at the same time. If you do that, of course, they all have to be compatible. They should all be LiDAR in this case. Just going to select that MRP file that I just drag and drop, and my output will go to this temporary directory. So the output, as you can see, is an MVR file. So we're creating a virtual raster, which in future you can just drag and drop into ProRaster Scientific and display it like any other raster, or work with it, or do processing from it, or anything else. And that virtual raster is going to implement a gridding operation. So that's why we call it a virtual gridding operation. So I'm going to turn off all these clipping options. We're going to do triangulation. My points are going to come from the Z band, so this is RL. This is LiDAR data, so I will need to choose a LAS query. And I'm going to choose one of these standard queries for ground, so it's going to select all of the ground returns from the pulse return data. I'll just set this back to this grid cell adjustment. I'll set this to 0. So our grid cell size at base level is going to be 0.5 meter by 0.5 meter. Hit OK, and we get a grid. Now, let's talk about tiling. So we've done triangulation, and I can tell you that this data set covers about half of the coastline of New South Wales. So it's this sort of very thin sinusoidal data set. And at the moment, we're seeing something fairly weird. It's because we are gridding tile by tile. And so at the edges of the tile, we'll see discontinuities between the data. Now, that's not a problem where we have lots of constrained information. In other words, we have points. But in this case, when we're looking at a very large scale, we can see the breaks between tiles quite visible. And that gives you a clue as to what's going on. So let's just explore that briefly. Now I want to go back and edit this grid that I've just made. So it's appeared onto this list. Here at the top of the list, here's the MVR that I've just created. I select it to edit it. And now I can change some properties. So you can see down here that there is a tile size. It's not labeled very well, but if you hover over it, says grid tile size. If I go to large and hit OK, then it's regridded, and you can now see that we're getting what looks like a convex hull, and that's what you'd expect if you did a Delaunay triangulation of some points. And at this point, the entire grid fits into one 248 by 248 tile, so we're getting a Delaunay triangulation. But you probably won't work with large tiles, you'll probably work with smaller tiles. And there are some advantages to doing that. Firstly, gridding is threaded by tiles. So each tile is generated by a different thread on your CPU. So if you have a Threadripper CPU with 32 cores, able to run 64 threads in parallel, then it's a good idea to use a small tile size so that you're generating more jobs that can be allocated to more threads and get the most out of your CPU. So I'm going to go back to a normal tile size, which is small, 512 by 512. With regards to tiles, we have this thing called padding. So when each tile is gridded, it's completely independent, but we want the data to match up along the edges of tiles. So what we do is we pad the tile. So we take a tile that's this big and we expand it out by a certain factor. That's your padding. And then we acquire all the point data within that entire pad. We grid the whole padded tile, but then we just take the data, we just keep the data that's inside the center of that pad, which covers the tile itself. That allows us to match data reasonably well along the edge of the tile. Now with triangulation, the data will normally match perfectly because it's generating the same geometry of triangles from one tile to the next, as long as there's some padding. So by default, padding will be enabled for this gridding method, and you can see that you can change the size of the pad from none through to large, and so that's doing a little bit of extra work in order to generate a higher quality grid by matching data along the edges of tiles. So we go back to looking like that. Now, as we zoom in, you'll see that the whole thing starts to change. So it's acquiring data from the MRP file. And as you zoom in, it's acquiring more and more data at higher and higher resolution. And so you see the grid start to take form, and you see the features remember that we're gridding ground, so we're seeing the roads and the hills and so forth. the features all start to take shape until you get right down to the highest possible resolution, where you're drawing from all of the returns that are in the LiDAR data. So that's the concept of virtual gridding. We can take a data set that's ungriddable, that contains 7.7 billion returns, and we can grid it because we're looking at it at a very large scale and we're taking only a subset of the points from the data file. But as we zoom in, we grab more and more of those points and we see more and more detail. Now, it all works on the fly on the screen. What if you want to generate a final grid, a hard copy that you can distribute to customers and other people, for example? Well, then you go to the raster processing menu and you do export raster. Select export raster, choose the MVR that you've just created, and then choose the resolution level. That 0 is base level, that's the highest resolution. Choose the format that you want to output to, and then it will go away and generate that grid at that full resolution for the whole data set. Now in this case, if I hit OK, it's probably going to head off and work for hours to produce the grid at that very high resolution at such a large scale. But that's how you get a final product out of virtual gridding. But in the meantime, what you have is a system that allows you to explore data without doing any large amount of work in advance, and to do a lot of QA on the data that you've received, and to find the problems before you go and distribute data to clients. Or if you're a client, you can find the problems that your contractor hasn't found, and you can go back to them and give them a blast. So let's continue to explore the options when gridding LiDAR data. Go back to our virtual grid. Here's our editor. So what we have there is not very good looking because we're not doing any clipping. There are 4 clipping options. These are all complementary. So if a grid cell gets clipped out by one of these options, then it will be clipped out. In other words, the clipping will be the intersection of these 4 different clipping methods that you can enable. The first one, and the easiest, is to clip to the bounding polygon union of the input MRP tiles. So the MRP file contains points that are stored in tiles. If a tile doesn't exist, there are no points there. So we can generate a clipping polygon that is the union of all those tiles, and so clip the data to that. So let's turn that on and see what happens. So now we have, as you can see, a much tighter clipping regime. We still have these polygons out, for example, generating polygons between this little island and the land. But you can see here that we've got actual sharp lines. These are tile boundaries. So there's no data out there beyond these tile boundaries. And so we're not generating any grid out there. So that's the first and easiest thing to do. Secondly, you can clip to a polygon. So you can browse to a map info format table, which contains a polygon. It can be an arbitrarily complicated polygon set. So there can be multiple polygons, they can have holes and islands and all the rest of it. They can be composed of millions and millions of points, and it will clip to that polygon in real time. So I'm not going to demonstrate that today. Thirdly, you can clip by distance. So in other words, if you're trying to generate a grid cell and it is it exceeds a distance threshold from an input point, then that grid cell won't be gridded. So let's clip by distance. And we have here a minimum and a maximum because we're gridding over multiple scales. So when I zoom right down to the highest resolution, that's when my minimum clipping is going to be applied. And as I zoom out, it will change. It will gradually change that clipping distance until it hits the maximum gridding distance, which will be applied, at this sort of scale. So let's set this to about 30 meters, and let's set the maximum to about 3,000 meters, and see how that changes the situation. So you see that it's just become a lot tighter. So all of those wild polygons that we had out over the ocean are starting to disappear because we're applying this distance-based clipping. So if we zoom in on somewhere, so for example here we have a lagoon, and at the moment at this level we're gridding across the lagoon. We're not clipping out that lagoon, but as we get closer, those polygons or the triangles start to break the clipping rules, and you can see that we start to make a hole in that lagoon, and as we go further and further in, that hole gets more and more well defined. Now if I go back to that clipping, let's say I made that only 15 meters at that highest resolution. Now you can see that I'm starting to generate holes in areas where really I would like it to grid across the whole. So here we have building footprints. We've got no ground returns. There's a hole there, and because of that small clipping distance, it has clipped out that hole altogether. So you need to make that adjustment to get a balance between filling holes that you want to fill in the ground returns and not gridding across areas that are voids or across water. So I'll go back to 30. The fourth option is to clip by filtering. I'm not going to demonstrate this. When you turn this on, you can select one of the bands in the data set, and then you can select a data conditioning filter to apply to that band. So at each grid cell, it's going to look, or at each point, it's going to, sorry, let me clarify. This is going to clip by eliminating points from the data set. And then the other clipping methods will then come in and apply. So if I had a line-based data set where I had survey lines and tie lines, and I only wanted to grid the survey lines, then I could, if I had a line field or I had a line type field, I could filter by that field and null out all of the points that are on tie lines, and thus remove them from the data set so that they won't get gridded. With LiDAR, you're probably not going to use that option, so we're not going to use that today. Okay, coming down here, we're still working with linear interpolation. Here's our method. We'll look at these other methods later. We've got our pad size, which is helping us to match data across tiles. We can select the band that we want to grid, and we can select the query that we're going to apply to our pulse return data to select returns, to select points that we're actually going to grid. Just some additional information down here in resolution and detail. So I can change the cell size of the base level of the grid to whatever I want. So I could change this to 0.25 by 0.25, for example. So 25 centimeter by 25 centimeter cell size. With LiDAR data, I usually don't use these options. Instead, I just use this grid cell size adjustment, and it tells me what the current grid cell size is, and it's derived from the MRP file that I'm working with. So it's currently 0.5 by 0.5. I can use this adjustment to change the grid cell size by a factor of 2 with each click. That's the first thing. Secondly, I have this point source resolution level adjustment. This allows me to change the amount of data that's being used to generate the grid at any level. So, for example, if I increase this value by 1, that it decreases the resolution. So I'm going to use less points. So let's hit OK, and we'll see this grid change to a lower resolution version. So you can see we've got more triangles now that are visible. We've used less points, 4 times less points, in fact. And just to further demonstrate that, let me then knock that down to, say, by 2 levels. Now we're going to bring in 16 times as many points as we were bringing in just before. And you can see that the resolution of that grid has increased. So there's a balance there. You need to choose some. If you pull in too many points, then you're going to reduce performance significantly. If you pull in too few points, then the grid might not look as good at every resolution level as you want it to. So you need to find that balance. And at the moment, we need to up it a little bit. We're putting in too many points, so we'll go back up to that source resolution level. Now, so that's triangulation. I won't say anything more about triangulation. Let's look at the first gridding method, which is the simplest, and that is nearest point to cell assignment. So this is like nearest neighbor. It will generate a Voronoi polygonization of the data set. And so each cell value will simply be assigned the value of the nearest source data point. So hit OK on that. And the grid changes. It actually takes a little bit longer to generate these things because it's doing point searches. And you can see that you get a slightly different texture. Now, out here, you can see the Voronoi polygonization, that effect in here and here. And you can see it here where we're getting this kind of tiling effect as we have fewer points in this particular area generating the polygonization. Whether or not you want to use that technique is entirely up to you, but one thing that you can do is you can use it to grid color. So I'll just close this down and let's go into the virtual gridding again. I'm going to use nearest. I'm going to grid color this time. Now in LiDAR data, you've got red, green, blue, and near infrared channels. The data won't always be present. The bands are always present, but there may not be useful data in them. It depends on your survey. In this case, we have red, green, blue. We don't have any near infrared. So we're going to choose red, green, blue. And the virtual grid operation, instead of outputting a single channel, say a 4-byte reel, it's going to output a red, green, blue, alpha, color, 4-byte color. So I'll choose all returns for my LAS query. I'm just going to hit OK. Now this time you can see that it's used an image layer to render the raster. We go into here. Our bands are, well, this is something I need to change. This should say RGBA. That's the composite color band. And then that's split into the red, green, blue, and alpha channels. We're just going to use this first one, that's RGBA. So if I zoom in, as we zoom in, you'll start to see that that it reflects the aerial imagery. So we've got our coastal imagery, houses and so forth, and as you zoom in you get higher and higher resolution. So so that's color gridding. You can also display this with a RGB color layer, in which case you can connect connect to those red, green and blue channels, and then you can go and modify the color stretch if you want to. So let's get rid of that. Go back to grid. Now I'm going to go back to, well, let's do something different. I'm going back to gridding Z. Go back to triangulation for starters. And now I'm going to choose a different LAS query. I'm going to choose this one, New South Wales Bathymetry. I'll hit OK. I'll come in here to the color component, just choose a color table suitable for this. Let me show you the LAS query. So here on the LAS query editor, I'll drop this down. I'll go to New South Wales Bathymetry. So I have created this query myself. The query rule is select by classification and return number. Then my return rule is all returns per pulse. So I'm looking at all of the returns, but I'm only looking at returns that are classified with this set of returns. So ground, rail, road surface, wire, and then from here, road surface, we go into wire guard, wire connector, bridge deck, and then extended classifications 21 and 22. In this data set, those things are not wire. They're not wire connectors or bridge. They are bathymetry returns, and so we're going to choose those bathymetry returns, and these can you can use either the names or you can use numbers, and then we have these other options. So we could filter by elevation, for example. We could take only the elevations that are below zero, in which case we're just looking at the below sea level. So that's our bathymetry return. Now if we zoom in, you can see that we've got land with a certain color scale, and then we've got bathymetry rendered in a blue color scale, and offshore you can see that we're getting bathymetry as well as land. So you can see the scalloped sand of this beach, and then out here you can see here's a bombora offshore, bit of a hole there where the top of the bombora is. You can see these rock platforms off of the beach, and here's all the bathymetry. If we come up a little bit, we'll find features like this. This is a shipwreck. This is a dive wreck. In fact, it's the HMAS Adelaide sitting in the sand off of Avoca. Now, so that's choosing a different LAS query. Go back in and edit again. Let's look at the next method that I want to show you. Now we're going to go to tensioned minimum curvature. When I turn this on, a new option pops up here called feathering, and feathering has a taper property. So when we tiles, at the tile boundary, when we use minimum curvature, it's not enough just to pad and join the tiles. There will be a visible seam along the edge of each tile using minimum curvature, because data is not so well constrained. And so in order to resolve that, we use feathering. So we're gridding out to the edge of the tile, and then out to the edge of the pad, and then instead of just discarding that padded data, we're actually blending the tiles together using that padded data in a feathering technique. So we use feathering, and the feathering uses a cosine taper. You can change the order of that cosine taper up and down if you wish. There are properties for tension minimum curvature. Here they all are. Let's not look at them for the time being. Let's just hit OK and see how that changes our data set. So now when I zoom in, triangulation artifacts will disappear, and we'll start to get a very smooth looking grid. So this is really the first time that it's been possible to use a more advanced gridding method like minimum curvature on LiDAR data. The vast majority of LiDAR data is gridded using triangulation. But now, with ProRaster Scientific, using the export raster option, you can output minimum curvature grids for LiDAR data at any scale. Now, it is important when using minimum curvature to worry about your cell size. With triangulation, you can use any cell size. You can make the cell size as small as you want. It doesn't matter, because all you'll do is get better definition on those triangles at maximum resolution. But with minimum curvature, it's different. You must choose a reasonable cell size for the data spacing. And usually we won't choose a cell size that's more than, say, 4 to 5 times smaller than the average data spacing. And so you're going to find yourself working with this grid cell size adjustment. So for example, I would probably say, put it up to say 1 meter. I mean, it could go down further, but it will start to become dotty and pointy. You'll see little points in areas where you don't have a lot of actual data. So I tend to go for a bit of a larger grid cell size. So let's have a 1 meter cell size. I'm going to bring this back down so that my point resolution is 0. In other words, at base resolution, at grid base resolution. That guarantees that I'm using all of the data. Hit OK. And so now going away, doing its minimum curvature. Minimum curvature takes a little bit longer than triangulation, so your computer is going to work a little bit harder. So what are the advantages of minimum curvature? Well, in areas like creeks, and I don't have time to really show you this right now, but in areas like creeks, often you have a low return density because there might be trees, they're blocking out the returns, so you're not getting so many ground returns. Your data is not as well constrained. When you do triangulation, you tend to build dams across creeks because it will triangulate across the channel because there's nothing in between, and so you'll build a dam using triangulation. Minimum curvature will tend to solve those problems for you. Those sorts of incorrect artifacts tend to go away. So that's one advantage, and you'll just find a better quality, smoother, more presentable grid at every scale with minimum curvature. So let me go into the minimum curvature property page. A bunch of things here. Just going to look at, I think I should reorder this. Firstly, iterations. Minimum curvature is an iterative process, and every iteration you do improves the grid a little bit, and there's no substitute for doing more iterations. So if you want a better quality grid, you can increase the number of iterations, in which case you may need to reduce the convergence so that it doesn't stop iterating. In fact, you can make this 0 if you want, turn the convergence to 0, and then it will guarantee that it will always do the number of iterations that you've asked for. Spline tension. So with terrain data, you might want to increase the spline tension from 0 a little bit up to around 0.25 or 0.2 is appropriate for terrain data. And that just reduces the overshoots and undershoots of the splines in the minimum curvature surface. So in other words, it will match the point data a little bit tighter. So on features like this on the edge of a cliff, instead of seeing a little bump on the edge of the cliff and a little dip at the bottom of the cliff, which is caused by splining, instead it will tighten those up if you use this spline tension. One final thing which I won't talk about very much, I'm going to do a video on gridding line-based data, and that's where this extraordinary new feature automated trend reinforcement is going to show its strength. Automated trend reinforcement, when used with minimum curvature, and can only be used with minimum curvature, it analyzes your data as it's gridding it. It looks for trends in the data. For example, this road is a nice straight trend in the data. The edge of this cliff is a trend. This creek line is a trend. It detects those trends and then it reinforces those trends in the data set. It doesn't generate a grid that doesn't match your point data, but it just generates a grid that matches the point data but enhances and reinforces those trend directions. So when you turn that on, most of your minimum curvature grid will not change visibly even at all, because the data is very well constrained most of the time. But some of these linear features will become more prominent, more well defined, and things like creeks, where you don't have good data definition because trees are blocking your returns, trend reinforcement will straighten up those creeks and give you a better definition of the creek channel, and that might help if you're doing water channel analysis. So I'm not going to turn that on now. When I turn that on, that will kick your CPU right in the nuts, right? Not only is it multi-threaded, it's superscalar. Your task manager will stop updating. It is really working your CPU. You're going to want a decent computer to work with automated trend reinforcement, but it does work in real time. You have to wait a little bit longer, but it produces very good grids. For LiDAR, it's not the primary purpose for that, but it can be used in LiDAR. So that's probably a very long ramble. I hope it gives you an introduction into how to use this system. You can use it to explore vast data sets in real time. You can find the problems, you can find the features, and at the end of the day, you can also use it to generate a final product, and a very high quality final product as well. Much better than probably anything else out there on the market. It's only available in ProRaster Scientific. You acquire ProRaster Scientific from the Microsoft Store. It's $200 US. You can install it on multiple machines. I think you can have up to 10 simultaneous licenses under your Microsoft account name. You can get a 7-day free trial, so you can give this a try. So if you have some LAS files or some LAS files, you can get a 7-day free trial of ProRaster Scientific. You can run your import and do some virtual gridding. At the end of those 7 days, you can decide whether or not you want to purchase the software. So thanks for watching.